The goal of this video is to extract the time course of calcium activity from each cluster that we identified in the previous video. That is going to produce a matrix that looks something like this. So this matrix contains, this data matrix has time on the x-axis, and the y-axis shows the cell number. Remember from the previous video, we isolated 79 putative neuron soma, so cell bodies. So 79, so each row corresponds to a different cell. And what we see here visualized in color is the time course of activity from each of those clusters. So just to make sure it's really clear how to interpret this data matrix, remember that in the previous video, we identified all of the pixels belonging to contiguous clusters, which we are now calling neuron cell bodies. So what we are going to do in this video is extract the time course of calcium fluctuations from every pixel, every individual pixel inside this cluster, and then we're going to average the time courses over all of these individual pixels, and that is going to give us one time course corresponding to the average calcium fluctuations from this cluster of data. So this gives us one row in our data matrix, and then we repeat that for this cluster, this cluster, this cluster, and so on for all of the clusters. So here we have 79 clusters, and that produces this matrix of 79 cells or 79 clusters over time. Now, when looking at this image, you can see that there are major differences in the amplitudes of the different cells. This comes from the inhomogeneity of the background of the microscope image data. Furthermore, you can see, particularly looking at this example time series, so this is the time series of one of the cells, that there are slow drifts. So there's a general increase in the brightness over time, and then maybe there's also a little bit of even a decrease over here. So we need to deal with both of these issues. We want to address both of these issues. So the first thing that we are going to do is transform the data into the change in fluorescence, which is often called delta F over F. So to do this, you divide each cell body's time series by the average over all time. So you can see that now the data are centered at 1 because the average is, well, we divide the entire time course by the average over the entire time course. So of course, that's going to be centered around 1. Next, we are going to apply a temporal filter to the time series data. In particular, we will apply a 5th order Butterworth filter. That is a passband filter from 0.5 Hertz to 13 Hertz. Now, temporal filtering is a major topic in signal processing and in neuroscience. And the choice of filter parameters is not trivial. In real analyses, you would want to make sure that this is an appropriate filter for these data. These are appropriate filter characteristics and so on. But for now, you can rest easy knowing that this is a pretty good filter for these data. Now it is time for you to pause the video, work through the partially completed Matlab code, and now I'm going to switch to Matlab and walk you through my solution. All right, let me start by closing these figures, which we don't need right now. So the first thing we want to do is get the time courses from all of the neurons or all of the cell bodies. So looking ahead a little bit, we are going to initialize our data matrix, and then we have a double for loop here. So we are going to loop over all of the cells or all the clusters that we identified in the previous video. And then we are going to loop over all of the time points, and then we are going to extract just one frame of data. So remember, this is the 3-dimensional data matrix that we created a few videos ago. So we extract the data, all the columns, all the rows, just this one time point. And then we want to get from this slice of time, this one video frame, all of the pixels, the average of all the pixels at this cluster at this time point. Okay, very good. So let's go back and initialize the data matrix. So we initialize this to be zeros, and now we have, what do we want this to be? We want this to be the number of clusters and then the number of time points. So that corresponds to islands.num objects, comma, n points. Okay, so now we have our matrix. We can have a quick look at the size and confirm that it is 79 clusters by 7,700 time points. Okay, so now let's complete this for loop here. So cell I, this is going to loop over islands.num num objects like this. And I'm going to initialize this looping index variable here to be 1. That's going to allow me to go through and start running individual lines from this double for loop without having to worry about running all of it at once, just in case there are some errors or some things we need to fix. Likewise, I'm going to initialize this for loop index to the first value, so time I equals 1. Now I'm going to get the entire map from only this one time course. Put that in a variable called tmp for temp, and I call it temp because, well, we only need it on these 2 lines of code. Okay, so then we want to compute the average of all the pixels within this time point. So here we have the image data from one time point, and here we have all of the cells, so the index to all of the pixels that correspond to one of the cells, so the first cell. Now, when we just run this, we can see that temp of these pixels is going to be a list of numbers, but actually this is not really correct, is it? We want this to be the average of all of these pixels. Okay, so that one is pretty easy to solve. We just have to add the mean function, and we can confirm that this gives us a single number here, a single value. Okay, so now I'm going to run through all of this, this double for loop here. So a few videos ago, we transformed the original data green, remember that was the cell array, to this data matrix data. And I mentioned in that video that sometimes transforming data from one variable type to another, in this case it was transforming from a cell array into a numerical matrix, that can facilitate some analyses. It might make other analyses a little bit more cumbersome or a little bit more annoying. And we actually see 2 examples of that here in this module. So transforming the data from a cell array into a matrix actually facilitated the image processing that we applied in the past several videos. So it made the processing easier. On the other hand, if we would have left the data as a cell array, that actually would have made this bit of code easier because we wouldn't have to isolate individual slices, time slices from this data matrix. We would only need to have one line of code. I mention this just to highlight the fact that sometimes the choices that you make while coding up data analyses are open to personal preference, and there's often many correct ways to write the same code to achieve the same goal in Matlab. Okay, so there's quite a big data matrix. It took a couple tens of seconds for this double for loop to run through. Now we are going to visualize some of the time courses. So we want to start by showing a plot, a line plot, of the time courses from neuron number 37. Now, there's nothing particularly special about cell body 37. I just happened to pick this number. Okay, so here we're making a plot of time vector by neuron TS. Remember, this is the variable we just created. It's cells by time. And we want the 37th neuron. So let's see what this looks like. Okay, so we get a figure, but it doesn't quite look like what I showed in the slides. In fact, there is actually one dot that's being plotted here. But the issue, the error, the mistake here in the code is that we are indexing only the 37th element, but that's not what we want. We want the 37th row and all of the columns. So in fact, it should look like this. Okay, so let's try rerunning this plot. And there we see the time course of fluorescence from neuron or unit 37, just like what we saw in these slides a few moments ago. Okay, so then we're going to show the image of all of these cells that we have extracted. And that's going to go in a larger subplot that's going to fill the rest of this figure here. So you can see the subplot geometry is 5 rows and 1 column. And now we are going to be occupying subplots 2 through 5. Okay, so let's see what this image looks like. Uh-oh, we get an error. What is going on here? Incorrect number of arguments. So it turns out that the image SC function requires either one input, so we could do this, or it requires 3 inputs, which is not what I provided. I provided 2 inputs. So the 3 inputs would correspond to the x-axis label and then the y-axis label, and then the color. So we have the color, we have the x-axis label. We need to provide something else for the y-axis. So we could say 1 to 79. This is actually not a really great solution because now we're hard coding the number 79. So if we would change our cell identification criteria, then this might not be 79. So, we could write islands.num objects. That would also be fine. But in fact, what I'm going to do is just leave them blank. So I'm going to provide an empty second input. And that means that Matlab is simply going to number this according to the index, which is the same thing as saying 1 to the number of neurons. Okay, so this looks good. And then I want to show you one other way of visualizing the data, which is to make a time series from all of the neurons at the same time in the same plot. So it's going to look like this time course here, this line plot, but from all of the neurons at the same time. And that's going to go into figure 6. So this makes it really, really clear that there are large offsets across all of the different neurons. Again, this comes from their physical location on the image, and there are these intensity inhomogeneities across the image frame. Okay, so now we want to convert to DF. So convert the data to the change in fluorescence over time relative to the average. Now, there's a few ways that you could do this. You could run this in a for loop. You could have a for loop that goes over all of the different clusters in this matrix neuron TS. I am going to implement this using the function bsxfun, which stands for binary extraction function. So we want to apply the function divide. The R here is for right. We're going to divide on the right. And we want to divide the matrix neuron TS, the time series, by the average of each neuron over time. So we are averaging over time. So we should make sure, I'm going to run this little bit of code here and make sure that this gives us 79 elements. This should be 79 elements because we want the average over time for each of 79 clusters. So let's see what happens. Uh-oh, this is a really large matrix. Now, why is this giving us a matrix? Let's think about the order of the inputs into the mean function. So the first input is the thing that we want to compute the average over. And the second input into the mean function is actually the dimension over which we want to compute the average. Now, what is the dimension that we want to average over? It's not neurons. We want to average over time. So in fact, this should be 2. So the fact that it was written as endpoints like this, Matlab was actually thinking that we want to compute the average over the 7,702nd dimension, and the matrix isn't actually that big. It's only 2-dimensional. So that's why we just ended up getting the matrix back. Okay, so let's try averaging over the second dimension, and now we see that we get, we can type whose ans is for answer. It's the last thing that Matlab outputted. And we can see that that is a 79 element vector. Okay, so that's good. That's what we want. Okay, and then we have a comment that says recreate the previous figure. And actually, I'm going to do both of the previous figures for comparison. Okay, so I want to recreate figures 5 and 6, but I don't want to overwrite figures 5 and 6. So I'm going to change this to be figure 7, and this one is going to be figure 8. And then I will run all of this code again, and that's going to create 2 new figures. So now we have, this was the neuron time series before converting to delta F, and here we have the same data but after converting. Now you can already see that the color ranges are more homogeneous across all of the clusters. This isn't really the best color range. I think it's still a little washed out. So if you like, you could try setting the color limit to this image. That's a little side exercise. Okay, you can also see that the change in brightness now over time is really centered around 1. That is quite different from the previous value where it was, ranged from like 400 to 600 or so. Okay, then here was the non-normalized fluorescence data from all of the clusters. And here you see the same for all of the clusters. Now, you don't really see 79 lines because they're all plotted on top of each other, which is good. That means that we have appropriately normalized out these large baseline shifts. Okay, so Remember, that was one step, that one processing step that we want to do with the time courses, was to convert them to delta f over f. The next thing we want to do is apply a temporal filter to the time series data. So again, looking ahead to see where we are going with this code, here we specify the filter band ranges in Hertz, and then we are going to create the filter coefficients using the function butter for Butterworth filter. And then in a for loop, we are filtering the time series data from each individual cell. Okay, so in the video, I said that the filtering should go from 0.5 Hertz to 13 Hertz. And now this says, so create the filter coefficients, this says check the help file for correct usage. Okay, so we are going to write help butter, and this is going to give us information about how to set up the filter. So looks like we need 2 inputs and so on. Now I've mentioned in a previous module that I actually prefer looking at the help file by opening up the function itself. So I'm going to select this function, right click and select open butter. All of the help file information that's printed here is also printed in the comments in the top of this function file. Now this is a built-in Matlab function. This is not something that you want to modify. In fact, it's not a good idea to modify these built-in Matlab functions. However, I find it more convenient to have the help file here rather than having to worry about, scrolling up and down in the command window. We have our 2 inputs. The first input is n, and this gives us the nth order filter. So I said in the slides that this should be 5. So we're going to set that to be 5. And then we can see the next input is wn. So wn is a 2-element vector with a passband of the 2 elements in that vector. Okay, that's very good. That's what we want. And then we see up here the cutoff frequency must be between 0 and 1, with 1 corresponding to half of the sampling rate, which is also called the Nyquist frequency. Okay, so this means that if we were to write in here filter range, this is actually incorrect. This needs to be normalized from Hertz into units of Nyquist frequency, which simply means that we divide by the Nyquist frequency, which is the sampling rate divided by 2. Okay, so this gives us our 2 sets of filter coefficients from the Butterworth filter. And oops, I think I didn't run this line yet. Okay, and now we're going to loop through all of the neurons, or putative neurons, all of the clusters that we have identified here. So I'm going to initialize a new variable called neuron ts filt. The ts, by the way, is for time series. So I'm creating a new variable. I'm looping over all of the rows in that new matrix. And then I'm going to use the filt function. This is contained in the Matlab signal processing toolbox. And we're going to apply the filter coefficients from the Butterworth filter to the neuron time series just from this individual cluster. Okay, so let's run this. And that goes quite fast. Filtering is a pretty fast operation. Now it turns out that you can actually do all of this with filt. You can filter the entire matrix, all the rows in this matrix, at the same time by inputting a matrix. So you can actually avoid using this for loop. I'm not going to show that here, but that's like a fun little side challenge if you want to work through that. Okay, so the last thing that we want to do is compare the time series of the pre-filtered and post-filtered data. And again, we'll stick with cluster number 37 just because today feels like a 37 day. Okay, so again, looking ahead at the code, it looks like we want to plot first the original time series and then the filtered time series. Okay, so the original time series was in variable neuron ts, and we know to get the 37th neuron, this is not the correct way to do it. We want to say 37 comma all. Okay, and then I'm going to copy and paste here, and then we want this to be the filtered matrix. Okay, so this looks good. Let's run all of this code and see how this looks. So what we see here is a warning message, something about extra legend entries. When we look at this plot, we only see one legend entry, even though we specified 2 of them. Let's zoom in here and see if we see both of the time series. We only see one time series. Now, this could happen if you plot two lines that are identical and they overlap, and then you only see one. However, I think something else is happening here. I think we're actually not seeing both of these plots. Now, what's happening here is that Matlab overwrote this plot, this line plot, with this line plot. So what we need to do is add the function hold on to tell Matlab that when you plot this line and then you plot something else on the plot, that should not erase the previous line plot. Okay, so let's try all of this code again. And this is looking a little bit better. Now the thing is, you see the original data up here, the delta f over f, and here's the filtered version of delta f over f. Now I would like to zoom in and try to compare these, but because there's this big offset between them, they're difficult to directly compare. Now we get this big offset because the filter that we applied started at 0.5 hertz, which means we filtered out the 0 frequency component, and 0 hertz corresponds to a mean offset. So what I am going to do for visualization purposes is subtract 1 from this time series here so that this blue time series is centered at 0. So let's redraw the figure, and then we see that they are overlapping. Okay, and now I want to zoom in and just kind of qualitatively inspect these two time series. So you can see they look really similar to each other, which is good. If the filtered signal looked totally wildly different from the original signal, then we might suspect that there was a bug in the code somewhere. And also the fact that they look so similar to each other tells us that most of the energy in this signal, most of what's happening in this time series signal, is already present between 0.5 and 13 hertz. So by excluding frequency energy below 0.5 hertz and above 13 hertz, we actually didn't remove that much from the signal. In fact, the main point here was to get rid of, if you look at the blue line, you can see this slow drift over time. That's something that I wanted to remove, and we were successful at that goal. Very nice. So now we have our time series that are normalized and filtered. We are ready for running some analyses, in particular a principal components analysis, and that's coming up in the next video.